So, so this seminar is more in like fluid mechanics, right?
No. We actually we try to cover as broader as possible. So we also have for people from solid mechanics or bio part, and some part from applied maths to do the method and development. So it's pretty broad. Not just focus on the fluid. So the reason we call this is the complex fluid and the soft matter. We cover both the fluid part and the material part and the solid part.
Okay, yeah. I hope my presentation today will be quite relevant.
Yeah, it fits
because because my major is in like geomechanics, geotechnical, and it's probably a little bit different from the conventional mechanical engineering.
Yeah, no worry about that. So
okay, on YouTube now, Joanne, do you want to start?
Yes. So Zheng, maybe do you like to try to share your screen to see if everything is working okay?
Yeah. I share my screen. Okay. So can you see my slides?
Yeah,
okay.
I can see that. No problem. Okay, we can start. So hello everyone, welcome back to our CFSM seminar today. So today we have Dr. Zheng Lai to give us a talk on coupled CFD and the DEM for simulating granular flows involving irregular shaped particles. So Dr. Zheng is currently an associate professor in the School of Civil Engineering at the Sun University, the SYSU University. Prior to joining SYSU, he was a postdoc research associate at SYSU during 2019 and 2021. And then he was joined like a research associate at Hong Kong University of Science and Technology and SYSU during 2022 to 2023 through the Hong Kong Scholar Program. He obtained his PhD degree from the Glynn Department of Civil Engineering at the Clemson University in 2018. He had also a short period of research intern at Idaho National Lab. His research interest is multi-physics, multi-phase, and multi-scale computational mechanics with numerical methods, including discrete element method, material point method, and the computational fluid dynamics, etc. So with that, let's welcome Dr. Zheng Lai to start his talk today. And Zheng, now the screen is yours. Please feel free to start.
Okay. Thank you, Jiaoyan, for the introduction, and thank you, Professor Zheng, for this invitation and organizing this excellent event. So, as Jiaoyan has already given the introduction, so I will skip this page. So today I will talk about two topics. The first is the side distance field based discrete element method. So this will be the method to model the solid the computational the contact dynamics of particles, and then the DM will be coupled with the computational fluid dynamics methods to simulate the fluid particle interaction problem. So first is the standard distance field-based DM. So the background is that the granular material is widely encountered in our like nature and also industry, and it has multi-scale characteristics. So for example, we are recently working on the coral sand. It is the major type of geomaterial in the islands in South China Sea, and two of the most salient features of the coral sand is that the shape is very irregular and it has abundance of internal voids. So the DM, as we know, it is a very like popular methods to model the contact dynamics of particles, but to incorporate the realistic particle morphology in DM modeling is very challenging. So over the years, we have developed some the irregular-shape particle models in the literature. For example, the Professor Angel Jose in Caltech have developed the level set DM. So it is applicable to model any types of particles. And also we have super ellipsoid, polysuper ellipsoid, and spherical harmonics, for example. But the development of irregular shape particle models is still a very heated topic, because some of the models are specialized in modeling a typical type of particle. For example, the super ellipsoid, it is more applicable to the round particles. And also, some of the particle models may have a very high memory consumption, and it is computational slow. For example, for the level set, it requires a lot of memory to store the level set values of a particle. So the critical step for developing a particle model and implement it in DM is to develop the contact detection and the resolution algorithm. So contact detection means to identify the contacts between particles, and contact resolution means to evaluate the contact geometries between two colliding particles. So the contact geometries will be used to calculate the contact forces. So the contact detection and the resolution step will take more than like 19% of the total computational cost of DM simulation, and the situation can be worse for non-spherical particles. And to approach this challenging, so recently we have developed the set distance field-based DEM. So the basic concept is that we use a set distance field generated interface to define particles. It has two basic functions. The first is the set distance function. So this function will return the set distance at every query point. And also we have the surface projection function, and it will define the projection of a given point onto the surface of particle. So based on the set distance particle interface, so the zeros set distance will be the surface of the particle. So based on the set distance description of the particles, we use the node to surface contact algorithm to detect the contacts between particles. So in this contact algorithm, one particle will described by the set distance, and the surface of another particle will be discretized into a set of surface nodes. So the contact detection will becomes to test if there is a surface node that intrude into another particle. So if there is a node inside another particle, the two particles will be in contact. So once two particles are identified to be in contact, we will need to calculate the contact geometries. So here we define a contact force at every intruding point, and for every intruding point, for the normal contact force, we adopt the energy conserving contact model proposed by Professor Feng Yingtian for evaluate the normal force. And for the tangential force, it is based on the conventional linear spring model. So I will skip the details here. So if you have interest in the details, we have the paper published recently published in the computational mechanics. So based on the set distance DEM, the general framework, we show that it can be flexibly used to model some conventional particle geometries. For example, here is the polysuper ellipsoid. So I will just go through the exemplified particle models here, and also it can be used to model polysuper quadrats and also the spherical harmonics. So here, actually in geomechanics, the spherical harmonics, because it can use the Taylor series expansion, like this concept to model actually irregular-shape particles. So it is very widely used in geomechanics to characterize like soils and sands. This particle shape can be also used in the SDFDM, and also the polyhedron. The polyhedron may be widely used in the mechanical engineering, and also the level-side particle model proposed by Professor Angel Jose. It is also applicable to the SDFDM, the general framework. So based on the SDFDM, there is another issue is that we need to discretize the surface of one particle into a set of nodes. So here shows several conventional methods to discretize the particle surface. For example, if we have a spherical particle, we can use the equal angle grid or the golden spiral approach to discretize the particle surface. For equal angle grid, we can see we have a lot of nodes at the pole area, so it may not be good for evaluating the contact force at the pole area. It will probably result in greater forces at this area. So for the golden spiral, it can provide uniform points at the surface of spheres, but if the particle is irregular, we can see due to the projection for the area that is close to the center of the particle, it will be sampled with more points. And for the area that is far from the center, because of the projection, it will be sampled with less points. So the uneven distribution of the surface points will result in like uneven contact forces. To resolve this problem, we proposed a weighted spherical centroidal Voronoi tessellation approach to discretize particle surface. So we can in the spherical particle, the space of spheres, we can use the centroidal Voronoi tessellation to discretize the parametric space. So if the area is close to the center, we can specify a greater weight. So after projection, it will its spacing will be regularized. So we just use the weights of the Voronoi states to control the density of the surface points. So here we will show some examples to demonstrate the performance of the SDFDM. So here is a simple random packing example. So here we have different types of particles, and we see that all types of particles can be modeled by the general SDFDM. And also we compare the simulated packing prosody with those of the conventional DM, because for ellipsoid, some conventional DM packages can model, and also we have physical experiments for to of the random packing problem. And so we compare the simulated packing process with those of physical experiments, and the results show the relative good match. And the second example is the column collapse. So here we use the spherical harmonics to model the irregular shape particles, and we can see the particles can successfully form a Sandel pair. Here is some snapshots of the column collapse process. In the third example, we show a nut that's spinning into a bolt. So the nut and the bolt is modeled by polyhedron, and it will result in multiple contacts between the nut and the bolt. So for the case of no damping and the friction, we can see the nut can spin freely through the tracks of the bolt. And we compare the spinning velocity with that calculated based on the analytical solution based on the energy of conservation, and we also see a very good match. So this example shows the good numerical stability of the SDFDM. The fourth example is the triaxial compression. This is a very conventional test in the geomechanics. So we have a confining pressure, and we compress the packing of particles from the top. And here shows the deviatoric stress versus the actual strain, and also the conventional volumetric strain versus the actual strain. So here we can see that for the volumetric strain, it will first decreases. So this means contraction, and after that, the volumetric strain will increases. So it means the packing porosity increase. That is the very widely observed the dialenticity phenomena in geomechanics. So I would quickly skip through the numerical examples just to demonstrate the performance of the SDFDM. So here, let's talk about the computational performance. So first is the memory consumption. So here we have shown some particle models, including the polyhedron, ellipsoid, the polysuperquadrates, spherical harmonics, polyhedron, and the level set. So these are very classical particle models used in DM. And we can see for polyellipsoid, polyquadrates, and spherical harmonics, because they only need some parameters to define the shape, so it will be memory friendly. And for polyhedron and the level set, it requires much more memory. And also for the computational efficiency, and we can see that for polyhedron, because if we want to calculate the set distance of a point to the surface of a polyhedron, it will require a lot of calculations to calculate the point to the triangles of polyhedron. So for polyhedron, it is very computationally expensive. So here we can see the level set is very computational efficient. So based on the memory consumption and the computational efficiency, we can choose the proper particle models for a specific simulation task. So also, can you hear my voice? Is proper? Okay. So we talk about the SDFDM. So this generic framework is applicable to any types of particles. And here we show this SDFDM can also be flexibly extended to model soft metal. So here we show the approach of coupled FEM and DM. So for a soft metal, actually we can regard it as a deformable particle. So here we can use FEM to simulate its deformation. And for the contact dynamics between each soft metal, each deformable particle, we can use the DM to evaluate the contact forces. So the procedure is that, so first we use the DM to calculate the contact force between each deformable particle. And then for each particle, we evolve the FBM to calculate the deformation. And then we go this procedure and we can simulate the contacts and the deformation of a pack of soft metal. Here is just two simple examples to verify the implementation of FEM. So here we have a brick and we can uniaxial pull this brick and also twist this brick. It's just to verify the implementation of FEM in our in-house code. And here is the expansion and the pull and the twisting of a membrane. That is which is modeled by triangular elements, and we can also see the simulation runs properly. Then we show some examples to demonstrate the couple in between FEM and the DM. So here we have a golf ball, and we shoot this ball with a very high velocity. It will impact with a wall. So because the ball is deformable, and we can see the velocity field and the stress field during this the impact process. And here we compare the simulated results with the physical experiments, and we can see that the velocity field is generally very similar, which verify the capability of the coupled FEM and the DM. And this example shows the packing and the compression of multiple deformable particles. So here we have two cases. The first case is with no friction, and the second case we have a small friction. For the case of with friction, we can see the particles are more like stable, and for the case of no friction, the particles can move more freely, and the vibration will be more notable. Here shows the stress field of the particles, and we can see at the contact point there we will have greater stresses. So these results show that our coupled FEM and the DM can be used to model the deformable particle problems. So actually, I'm more interested in developing mathematics and also the algorithms. So here I just use some like very simple example to demonstrate our developed algorithm and also the software. So these examples are very simple and may not be like have much physical meanings. So here we also want to show that if some of you have an interest in using this software or algorithms, we can give some, we can collaborate or give some suggestions or to work on some real problems. So for the first part, I described the SDFDM, which is applicable to any types of irregular shape particles. And here, in the second part, I will show how the SDFDM can be coupled with CFD to model the fluid and granular flow of irregular particles. So here is a little bit about the background. So for CFD-DEM, we know we can have basically two types of strings: the resolved CFD-DEM and also the unresolved CFD-DEM. So for the resolved CFD-DEM, we can model the particle shape in high resolution, and the particle fluid interaction force will be modeled in very high resolution. And for the unresolved CFD-DEM, the particles will regarded as points, and the particle fluid interaction force will be evaluated based on some empirical like drag force models. So here for the CFD-DEM, we just want to develop a complete tool that can simulate any problem with large particles or fine particles. So here is a brief introduction about the formulation of unresolved CFD. So for the governing equations, that's very basic, the NS equations. So I will skip the details. So for the unresolved CFD-DEM, we just use the drag force models to describe the interaction force between particles and the fluid. So the force from the particles to fluid will be modeled by a source force in the NS equation. And for the force from the fluid to the particles, it will be modeled as an external force to the particles. And for the semi-resolved CFD-DEM, because for unresolved CFD-DEM, it have a restriction on the mesh resolution to the size of the particles. It requires that the mesh size of the fluid that is at least 3 times of the particles. In that case, the drag force can be correctly calculated. And for the case of our mesh resolution is very close to the size of the particles, we cannot use the unresolved CFD-DEM because the porosity and also the velocity, these variables cannot be properly calculated, because for the cell we are as shown in this figure. So for fine mesh, a mesh cell may be totally overlapped by a particle. So the porosity that is required in the calculation of drag force will be 0 or 1. So this will result in inaccuracy in the calculation of drag force. So here, for the semi-resolved CFD-DEM, we just use interpolation function. We regard a set of mesh cells as one single cell, and we use that one single cell to calculate the drag force. So based on this averaging and the interpolation, the semi-resolved CFD-DEM will be converted into an unresolved CFD-DEM. So actually, there are a lot of literature on the unresolved CFD-DEM, and our main contribution is on the resolved CFD-DEM, because most existing researches on resolved CFD-DEM mainly works on the spherical particles. So here we extended the conventional resolved CFD-DEM. We integrate the CFD-DEM with our SDFDM to provide the capability to model irregular shape particles. So in the resolved CFD-DEM, we have the conventional NS equation, and also the motion of particles is described by the DM. So for the interaction between particles and the fluid, we use the immerse boundary method to calculate the particle fluid forces. So there are two main procedures in the immerse boundary method. So when we calculate when we solve the NS equation to account for the existence of particles, we will need to correct the velocity of the fluid cell that is overlapped by the particles to the velocity of the particles. So this means for the fluid that is overlapped by particles, their velocity will be corrected, so it will move with the particles. And the second step is that we will integrate the stresses on the particle surface to calculate the force from the fluid that applied on the particles. So if a particle is in a fluid, the fluid will have some forces on the particles. So that's the basic concept of the result CFD-DEM. So if you have any questions or I'm too fast, you can just stop me. And for the implementation, for the fluid, we adopted the open form to solve the NS equation. And for the DM part, we have our in-house code NetDM. So we implement the coupler to exchange the information between CFD and the DM, and all the simulation results can be rendered in the pilot view. Here, I will show some verification examples of the CFD-DEM to show to verify our implementation. And for the unresolved CFD-DEM, because it is conventional and also available in some open source package, for example, the CFD-DEM. Here we use the library experiments, the 10K test to verify our implementation. And we can see in this example, we have a particle. If we release the particle in the fluid, it will settle and reach inventional terminal velocity. So this terminal velocity can be used to calculate the drag force coefficient, which is required for many CFD-DEM analysis. As we have mentioned, for the unresolved CFD-DEM, it has a restriction on the mesh resolution. It usually requires that the mesh size is at least 3 times of the particle size. So if the mesh size becomes smaller, the evaluation of drag force will be inaccurate, and we see it will result in very large vibration in the particle velocity. So for the semi-resolved CFD-DEM, we can see for any cases of mesh resolution, it can handle properly. Here is the organ test. So in this test, we have a pack of particles. So we have the water injection from the pattern. If we increase the injection velocity, the pressure we require to keep this injection velocity will also need to increase. In this case, we have a critical inject velocity because if we go beyond this critical velocity, the particles will become fluidized. So it is a very conventional test to verify the implementation of the CFD-DEM. So here we also compare the simulation results with the analytical results, and we can see a good match. So these examples shows the good performance of the unresolved CFD and the semi-resolved CFD. And here I will show more examples about the resolved CFD-DEM and also the case of irregular-shape particles. So for the first example is the settling of super ellipsoid particles. The setup of this example is very similar to the conventional particle settling test, except that the particle shape is irregular. So for different particle, here we use the super ellipsoid particle. We can see that for different flatness, the particle will have different settling velocity, the terminating velocity. And here we use the resolved CFD-DEM. In the resolved CFD-DEM, the particle surface can be resolved in high resolution. So it is different from the unresolved one. Here we can see that the simulated results also matches well with the physical experiments.
So Dr. Lai, I have a question about previous test case. So what happened with the boundary? I see there's boundary have.
Yes. I also noticed that. So here, I think I showed the velocity field, and the top part there is the free surface. So I think it is some vibration of the water surface.
Okay, there's free surface. Okay.
Yeah, there is a free surface between the water and the air. The second example is the oscillation of cylinder in a free stream. So here the cylinder is enforced to move in a sinusoidal motion, and we can calculate the force that is required to keep this motion, and we compare the simulated results with the physical experiments, and also the results show a good match. The third example is the wedge that enters into the water. So here we model this problem in 2-dimensional, and the wedge is modeled by the polyhedron. And we also compare the simulated results with physical experiments. And for the evolution of velocity, there is some differences, but the overall trend is similar. So after our investigation, we speculate that the little difference may result from the fact that the real physical experiments is 3-dimensional, and here we use the 2-dimensional for modeling this example. Well, these are very basic verification examples. We compare the simulation results with the physical experiments. And here we will show more illustrative examples to demonstrate our developed CFD-DEM to model multiple irregular-shape particles and their interactions with fluids. The first example is the column collapse. So here we consider 3 cases. The first case is the jet case, and the third case is the fully immersed case. And in this example, we just want to see how will the particles interact with the free surface of water. Here is some snapshots of the 3 different cases.
Can I have a question?
Oh, yeah.
So can you back to the previous.
Oh.
Yeah. Let's.
Okay.
So the third one is from VOF results.
Oh, all these are simulations. The third case is the fully immersed case. The red color shows the volume fraction of the water.
Okay, so there are no phase,
no air. Yeah, the third case is no air. Yeah.
Oh, okay. Thanks.
Okay, so here we observe a very interesting phenomena here. So for the case of partially immersed, so we can see that to begin with, the water will be pushed away, and after that, the water will come back. So it will result in a concave profile of the final centropile. So if we further investigate the macro parameters of the particles, we can see that for the case of fully immersed, the evolution of velocity is slower than the case of the jet case. So because the water, for the case of fully immersed case, to begin with, if the particle moves, it will bring the fluid to move. So the kinetic energy will transfer into the fluid. And when the particles becomes to come down, the kinetic energy will transfer from the fluid to the particles. So for the case of fully immersed one, we can see the evolution of velocity is slower. And we can also investigate the contact force strength. So here I will not go through deeper. The second example is the bed load transport. In this example, we have a pair of particles, and we inject the slurry from the left side. Here we consider two different cases, one with relatively slow injection velocity and the other with relatively high injection velocity. So here shows the simulation animation. And here we can also observe interesting phenomena for the case of low velocity. So actually the particles on the backside of the centropile will move first. And for the case of high velocity, the particles that is in the injection side will move first. So these are the snapshots. And the last example is the sufficient problem. So as we have mentioned, we have the unresolved CFD-DEM and also the resolved CFD-DEM. The unresolved one is more useful to model very fine particles, the large particle systems. And for the resolved CFD-DEM, because it is conventionally expensive, so it is usually used to model coarse grains. So in this example, we show that we can combine the unresolved CFD-DEM with the resolved one to model the case with gap-graded particles. In the sufficient problem, we have a skeleton of coarse grains, and we have some fine particles. With the fluid flows through the skeletons of the coarse grains, the fine particles will move with the fluid. So this is the sufficient problem, which can be observed in the erosion of coastal. Here is the simulation results. So we can see the as we have described, during the sufficient the particles will move through the skeletons of the coarse grains. So these phenomena were captured by the simulation. And we can also observe that some particles can be trapped by the coarse grains. And here we consider 3 different cases. So we compare the case of irregular shapes with the spherical case. And also we have a case that the fine is larger with a smaller ratio of coarse grain size to the fine grain size. We can observe that if the size of fine grains are greater, it will have large chances to be trapped in the voids of the coarse grains. So here is some quantitative analysis. So we can see that for the case of spherical particles, the rotation rate is actually the amount of fine particles that is remain in the voids of the coarse grains. So for the case of spherical particles, there will be less particles that is trapped in the grains. And also with the increase of the fine grain sizes, the rotation rate will decreases. That means if the fine particles is smaller, it will have less chance to be trapped. So here we also consider the case of different flow velocity. I will just skip this. So I will give us a brief summary. So in the first part, we have talked about the static distance field-based DM. So this approach is applicable to any classes of particle shapes, including the widely used spherical harmonics, polyhedron, and also the level set. And also in the SDFDM, we use the energy conserving contact theory. So it is very good to the numerical stability and also enables quantitative energy analysis. And we have also shown that the SDFDM can be flexibly extended to model soft metal. And in the second part, we have shown the coupled CFD-DEM within the SDF framework. We have shown some numerical examples of the resolved one, unresolved, and also the semi-resolved. So based on these 2 topics of research, we have developed a complete tool that can simulate the fluid and the particles. And all these algorithms are developed in our in-house code. We call APAAM, the Applied Process Analysis and Modeling. Yeah, so that's all for my presentation. You are welcome for any question and discussion. And also, if anyone has an interest in collaboration, and we are also very welcome.
Yeah, thank you, Zheng Shou, for the very interesting talk. So with that, I think we can start our question and discussion. If there is any question from the audience, please feel free to unmute yourself and ask your question here.
So Zheng Shou, I have a question. Thanks very much for your talk. Very interesting to me. And I have a question for the first part. When you use the assigned distance method, so I can understand how you could determine the distance when you use the projection. But when you have the irregular shape, how you define the normal direction? So this will be locally determined, or what kind of method you are using to determine the local structure of the normal direction? Because this will determine how you do the projection, right?
Yeah, yes. So here, for the normal direction, actually, we adopt the energy conserving contact theory proposed by Professor Feng Yintian. So here, he used a contact potential to like for each contact point, it has a contact potential, and this contact potential is a function of the relative position and also relative rotation between 2 particles. So for the contact force, it will be the derivative of the contact potential with respect to the relative position. And for the contact moment, it will be the derivative of the contact potential with respect to the rotation. So here, if we have calculate the contact force, so the contact direction will be the unit vector of the contact force. So the contact, normal direction is evaluated in this manner.
Okay, understand. This is modeled, right? This is not directly calculated by the particle positions. It's modeled by interaction potential, right? So this
So it is not it's not like defined manually. It is evaluated from the contact potential.
Okay. So I have another question about your CFD and DM coupling. You use a semi-resolved method to sieve the computation, but I'm wondering when you use the semi-resolved particle, how you can define the no-slip boundary condition on the particle surface, or because the particle emerged in the fluid part is not just a Forsen term. Because this particle will also affect the flow direction because the no-slip boundary condition. And if you change the particle geometry, then the local flow field will change. I'm not sure when you have, if you fully resolve the geometry, I understand how you implement the no-slip boundary condition. But when you have semi-resolved particle, how you can determine the no-slip boundary condition, or how the shape change will change the force and turn, and also change the flow field. How you handle
that? I see. Yeah, it is a very technical equation. Yes. So actually, as you have mentioned, for the resolved CFD-DEM, we have so the non-slip boundary condition can be approached by the immersed boundary. And we have also done a lot of analysis, a lot of investigations to investigate if the non-slip boundary condition can be also probably accounted for the case of irregular-shape particles. And honestly, for the unresolved CFD-DEM and also the semi-resolved CFD-DEM, we haven't done more detailed investigations. So previously, our main contribution and the main focus is on the resolved one. And so for the unresolved and the semi-resolved, I think the non-slip boundary condition issue can be an issue. I don't have an answer for now. Yeah, it is an interesting question, and maybe we will investigate this issue in the future.
Okay. So Dr. Lai, are you available to after this meeting for discuss for 10 minutes?
Yeah, I'm available. Yeah, no problem.
Thank you. We will talk later.
Okay.
And Zheng, in fact, I have a follow-up question on top of Zheng's question. So for the like DEM, like the interaction part. So I'm just wondering. So it seems you're gonna to use a potential energy to compute the interaction force. So I'm just wondering how you determine the coefficients of those kind of force constants.
Oh, so for the GIDM,
like if you go back, if you go back to your formulation, so here you have a Ki, right? So how you determine the Ki's for different system?
Okay, yeah. So in the conventional DM, we have two popular contact models. One is the linear spring contact model, and the other is the Hosian contact model. So for the contact potential-based contact model is because the force is determined by the derivative of the contact potentials. So it is the final force and the displacement profile is not very straightforward. So here we have to some investigations and propose two types of contact potentials. So one is called the linear contact potential, and also is another is the 3 by 2 the power contact potential, and we have derived that these two types of contact potential can be similar to the conventional contact models, and we have established a relationship between the contact parameters in the contact potential between the contact parameters, the coefficients in the conventional contact models.
Then are you able to match the say Young's modular and some kind of shell modular with the calibrated like coefficient of
Yes. For the case of spherical particles, the coefficients can be well matched. But for the case of irregular shape particles, because there could be multiple contacts, actually the contact force, the contact model is not properly defined for the case of irregular shape particles, and also with multiple contact points. So for the case of irregular shape particles, the conventional linear spring and also the Hossein contact model is not directly applicable.
I see.
Yeah.
And so far, seems the potential can only catch the elastic part, right? Say if there is any viscous effect or plastic effect, so we have to enrich the potential here to capture the plastic force or some viscous force accordingly. I see. Yeah. And my second question, in fact, is regarding the, so you mentioned the level set method at the beginning of your talk, and then you also developed this SDFDM. So I'm just curious, so besides the computational effort, is there any like a significant drawback that you have observed for the level set method comparing with the SDFDM?
Oh, actually, SDFDM and level set DM they are not two different approach. We would like to show that the SDFDM is a general framework, and the level set can be cast into this framework. So in the SDFDM framework, if we use the level set particle model, it will fall into the conventional level set DM we know. And if we use other particle models like spherical harmonics, it will become a different approach. So based on the computational performance, the level set will request much more memory, but it is very computational fast. And for other particle models like spherical harmonics, we just need very little memory, but it is more expensive.
I see. Yeah, thank you very much for that further explanation. So my last question, in fact, is just about the different like particles. So you mentioned 3 types, like unresolved, like semi-resolved, and resolved particle, right? So can we consider according to your current framework, do you consider the unresolved case just as a mathematical point? So you just you don't consider the shape of the particle, so it's just a mathematical point. So you do the interaction, calibration between the fluid and the particle. So how do we consider this unresolved? I'm not sure if my understanding is correct. So it seems you mentioned some drag force and some force to describe the interaction between the fluid and the particle, but I'm not sure what's the main difference between the unresolved and the resolved cases.
Okay, Yeah, so for the unresolved CFD-DEM, so because it is termed unresolved, in this case, the particles we can regard them as points. They have no real shapes or real sizes or volume. So it will be a points in the domain of fluid. So to account their existence in the fluid domain, the forces will be characterized by the drag forces, and also their existence will be accounted for by the porosity. So, for example, if we have a lot of particles in the domain, the porosity will be greater. So, these aspects will reflect the existence of the particles. And for the case of the resolved one, so the shape of the particles will be modeled. So based on the figure, yeah.
Right,
so
right. Then for your sorry. So for your unresolved case, so if you just consider the particle as a mathematical point, then how you determine the contact force between the solid particles? Like you have to know the radius, and so you can determine the contact force. If they are just a mathematical point, how you determine the contact force?
Okay, so actually here, the CFD will be solved, and the CFD and the DM will be solved independently, and they will just exchange the forces. So for the unresolved CFD-DM, in the DM part, the particles will have their conventional the size and also the radius, the position.
I see.
So
okay,
when we approach their interaction, they will be regarded as the points.
Yeah, that makes sense. Yeah, thank you very much for that detailed explanation. I think we also got a question from the chat from Alex, and he is asking that based on your experience, do you think that spherical harmonics is the best approach to the random shape geometries of the particles? And are there any other techniques in order to simulate accurately this complex geometry, maybe with artificial intelligence model, physics-informed neural network, etc.? And the second question is, in order to simulate problems in this scale, we need mostly, as it seems, computational clusters. Is it possible to run simulation in common personal computers and have the expected results comparatively with laboratory experiments?
Okay, I think the second question is simpler. I will answer the second question first. So here, the open form is it had the code Open MPI parallel feature, and also our in-house code NetDM. It is we have also implemented the Open MPI and the MPI parallel, so they can run in clusters or HPC. So it is doable. And for the first question, based on our experience, the spherical harmonics is we think is the best approach to model arbitrary irregular shapes, and it is also used to generate virtual particles, because we can regard the coefficients of the spherical harmonics as a set of variables, and we can use the random field approach to generate a new set of coefficients, and it will be corresponding to a new virtual particle. And also, recently, we are also exploring the machine learning approach to describe the particle shape. In the computer graphics, they have used called deep SDF. They use artificial neural neural network to infer. It's like a black box to infer the set distance of each point. So we do not have analytical function, analytical formulation to calculate the SDF. It uses ANN to calculate the set distance. So we are not exploring this direction, and I will probably present this topic in the EMI in the June.
Oh, you will come to US in June?
Yeah, I'm working on the visa now. If I can
Okay.
get the visa successfully, I will come.
Okay, great. Good luck on that.
Yeah.
Okay, great. I'm not sure if we have more questions from the audience. If not, I think we can stop here and finish our today's seminar here. And with that, we would like to thank Dr. Zhenshuo Lai one more time for the very interesting seminar. And with the CFSM community, we'll have more seminar later on. Please pay attention on the further announcement. And with that, Zhenshuo, maybe you would like to stay for a longer time after the seminar, and we can do some private discussion. Okay, with that,
sure.
let's just close the